Good morning, everyone. Welcome to the Tuesday Refresher. I'm Jim Chastain with EasyPower's application group, and I wanted to welcome you to this second part of this presentation, which is focusing on the list of top 10 mistakes in arc flash studies. And we started off with a full list, but we're only able to cover half of it in the first session, but it included a description or discussion on the arc flash paradox, the fact that if you approach the project a little slower, you can end up with better results, that there's some reason to be concerned or at least aware of the different characteristics of buses, that the infinite source is not the worst case in arc flash calculations, and it has been determined that contrary to the recommendation in the original 1584 model, 240 volt systems in some conditions cannot be ignored. So I invite you to reflect back on the first recording we have of this presentation. So let's jump into the second half of the list. Number 6 is the misapplication of the 2-second rule. And there are some people that balk at the terminology, saying it's not a rule because it's in the informative annex of NFPA 70E. Well, here's what the verbiage says in the 2018 version of NFPA 70E Informative Annex D. Greater than 600 volts open air bolted fault current may be high. Consider how long a person is likely to remain in the location of the arc flash. If it is likely that a person exposed would move away quickly if possible, or it is likely they will move away quickly as possible. So 2 seconds is a reasonable maximum calculation time. Use sound engineering judgment. So that was greater than 600 volts. Then again in Article D4.3, if the arcing time in equation 4.3 is longer than 2 seconds, consider how long a person is likely to remain in the location of the arc flash. 2 seconds is a reasonable max calculation time. Use sound engineering judgment. So that's the verbiage. And again, some people refer to that as a 2-second rule. But the fact that it's included in the standard model itself, and again, it's been repeated in the most recent release, 1584-2018, where it says if the total protective device clearing time is longer than 2 seconds, consider how long a person is likely to remain in the location. And if they have the ability to move away quickly, it's usually 2 second max is a reasonable assumption for the arc duration. Well, I guess my contention goes to the discussion about how to apply sound engineering judgment. And in my opinion, I would want to know what the worst case arcing current actually is, because the higher that current is, the more energy will be delivered in a shorter amount of time. So the question that I suggest I would want to answer before limiting any time was to understand why the clearing time is so long. Now, specifically, because the low voltage or less than 240 volt systems were maligned in or at least ignored in the first 1584 model, it's now been reflected that if the current is above 2500 amps, that we really do have a possibility of an arc flash event, and we need to make sure before we start ignoring things what the actual calculation time is. Then the other question to ask is, in limiting the time, is the intent based upon somebody's ability to remove themselves from the area, is the intent just to have PPE cover them for that 2 seconds that it takes to get blown away, or will they be consumed or in the conflagration that's going to happen during that 2 second period? None of which is easy to answer, and that's again why the recommendation to use sound engineering judgment. So what I've done is I picked a file from the archives, and this looks like it's about a 700 or 800 bus system from a steel foundry or some sort of a metalworking operation. And I wanted to see how they set up their short circuit options. So as we look at this, there's two things I actually have a problem with. One is he's talking about including his main in all of his system. These are global settings. And second, they've limited their max calculation time to 2 seconds for all voltages. So I want to do a little exploring to see how that affects the results. So we've done a fault all the buses, look at the display for arranging for arc flash, and sure enough, even in the 480 volt section, I see areas, a couple buses here for starters, that actually have limited the calculation time to 2 seconds. So I want to dig in a little bit deeper to see what the situation is for those specific buses. And I think the first one is furnace number 1 CP. So let's find that in our one-line diagram and look at how the calculations change if I remove that 2 second limitation. So it looks like there's 16,000 amps going into what appears to be a furnace, and it shows 65 calories being calculated, and we know that's based on the 2 second limit. So let's kind of go in and change that 2 second limit to something higher. In this case, I'm going to use 100 seconds just to allow the calculations to run the full range, and then see how that impacted the energy on this particular bus. So let's focus in on this one and look at the range for arc flash display. And what I see is that it's a 480 volt bus, that the air gap is nominal for that voltage, and yes, indeed, the incident energy goes up dramatically, almost an order of factor of 10 compared to what was in 2 seconds. Now, in either case, the recommendation is not to work on the equipment while it's hot. So, in my humble opinion, the primary reason for using the 2 second limitation in this case was not based upon safety, because we're not going to allow anyone to work on this system while it's hot. But by limiting the calculations to 2 seconds, it does prevent outlandish results on my one-line diagram, which may be either a policy statement or a goal that I have based on the corporate maintenance philosophy. But in either case, the expectation is there will be no hot work on this particular system. So another element that popped up when I was looking at this was in the 240 volt system, and it was 2 comp dis. So let's kind of look at that. If I slide this down, 2 comp dis. Now this is a bus that's showing high incident energy, and I know it's limited to 2 seconds, and we're showing it's fed by a breaker, and the arcing current looks like it's 7,000 amps, which is substantial even in a 240 volt system. So my question is, why is it taking so long? If we're limiting this to 2 seconds and really it's going to take 10 seconds for the protective device to trip, why? What's the problem? Well, to be able to examine that, I'm going to pick out this bus, these cables that are the connection point all the way up to the breaker itself, and then let's go into a coordination mode and plot the time current characteristic curves, and blow this up a little bit by removing the title block. So I can see here that this golf club shaped plot is the trip characteristics of that breaker, and if I fault the bus, the tool, by right-clicking on the trip curve, the tool will show me what the arcing current is for that bus. We've got 23,000 amps volted fault current, and coming through that bus should be 21,000 amps. If I right-click on this plot and insert arcing current, I can see that the current used for calculating incident energy falls in the vertical band of this trip unit. And this explains why the manufacturer cannot guarantee that this unit will clear until that current crosses the right-hand side of the plot. And that's where we get our 10-second number for calculations. So this explains quite a bit. So if we hover over the plot again of that breaker, we can see the adjustments. This is a low voltage power circuit breaker. I can left click and drag and readjust or show what would be the effect of readjusting the set points on this breaker. And now my arcing current falls in the instantaneous trip settings for this breaker, which would allow it to trip much faster. So we still have the same arcing current, but now when I go over here and look at instant energy, I can see now my instant energy on this bus is down to 1.4 calories, which indicates a number of things. So if we go back to our display now with this setting on our protective device, we fault this bus and arrange for arc flash, we see that we still have the same current, both the fault current and the arcing current, but now the calculations are not, it's not necessary to limit them to 2 seconds. In fact, the breaker is going to trip normally in 50 milliseconds, which provides 1.4 calories of protection. So in this case, by applying the 2-second rule, I've actually obscured the fact that we have miscoordinations and the ability to mitigate the incident energy on a bus that is a real hazard, and frankly provide some measure of protection if we need to work on that system. So again, it's a misapplication of the rule, and I think it bears notice for someone doing the study. Number 6, the main breaker will not fail, so I never exclude it. We saw this in that previous one-line diagram that I looked at. He had a setting where all of his main breakers were included in the calculations. IEEE 1584, the latest version, and this verbiage was in the older standard, it says an integral main overcurrent protective device may be considered in the calculation if it is adequately isolated from the bus to prevent escalation to a line-side fault. When the integral main current protective device is not adequately isolated, the upstream protective device must be considered. So the decision to include or exclude has nothing to do with whether or not the breaker will fail on its own. It has everything to do with the physical construction of the panel or the MCC itself. So think for a second or consider what happens during an arc flash event. The radiated heat in the concussion blast is driven by the expansion of copper as it vaporizes due to the heat in the plasma ball. The source of the heat is a plasma ball which is surrounding the arc. And that plasma ball, because it's ion rich, has the potential to ignite a second arc on any buses it touches. And that means it can render the main breaker useless given the right conditions. So if the cover is removed and there's no flash barrier between the hot bus that I'm working on as an operator or technician, and there's no barrier between me and the bare conductors coming into the main breaker, then that means the calculations must depend on the performance of the next upstream device. So let's see how this looks in real life. We have a typical radial system. If I'm going to work on this bus 2, take the cover off the panel, if there's not a barrier between me and the incoming conductors of this breaker, then I cannot rely on the performance of that breaker adequately protecting me as a worker. So to illustrate that point, I'm going to fault this bus, go into short circuit focus, isolate this particular bus, and then look at instant energy. And if we arrange for arc flash to show how these calculations were made, we see it's a 480 volt bus. We see the switch gear, we see the bolted fault current, but the calculations were utilized using BL5, which is the next upstream device. And that's due to the fact that in our short circuit options, we've excluded the main in calculations. So that's, again, an error that's overlooked in a lot of studies. In most of the 480 volt bus panels in the United States, there is not an arc barrier between the incoming conductors and the main bus. So I fear that this is an error that's made in most cases. Now, sometime last year, I had a response when I went over this point in a webinar online that now the National Electric Code includes a requirement to have a barrier. Well, as it turns out, if you look at Article 408.32, it describes in the NEC, it describes barriers to prevent inadvertent contact, but manufacturers will be quick to acknowledge that these are not arc flash barriers. In most cases, they're plastic covers that cover the terminal, and it's true that one of the most frequent sources of an arc, initiating an arc, is inadvertent contact with live terminals. So there is some potential here for preventing the initiation of an arc, but in fact, if an arc were to be in this area, these barriers would not be an effective arc barrier. So just so you know. So number 8, no system change from the initial study. We got a call. A customer we done a study for 5 years ago calls up and says, hey, there's nothing changed in our system. Just rerun the equations and send me new labels. Well, okay, if that's what you want to do, but are you really sure nothing's changed? Are you sure that on some swing shift or graveyard, one of the maintenance people had to replace a fuse and he used what he had in the truck or in his toolbox just to keep the system up and running, and then he failed to document that change? And worse, what if he just had one of the phases had a replacement, and so now I have a potential different value in different phases in some part of my system? Am I sure that no relays were tweaked by an off shift and not documented? And for some reason we were getting intermittent fails or trips on a relay, and the electricians knew that if they just tweaked some of the settings, it would prevent those trip settings. But as soon as they do that, they've changed the arc flash results. Are we sure that there's been no changes in the utility data? Has there been any new buildings built in our area, in our region? Have there been no new transformers or substations put in around us? The utility is under no obligation to notify us when they change something. So if there's been a new data center built in the area or a new manufacturing plant in the neighborhood, it may be that the available short circuit current has changed in some cases dramatically. And again, the utility may remind us, well, just use an infinite source. And yet that's not the worst case for an arc flash. It's actually the lower available fault current that could cause us a problem. And then if there are new transformers in the mix, it will affect our X over R ratios, and the ability to exchange energy will be different. Consequently, it will affect our arc flash calculations. So at the very minimum, when it's time to update your study, you want to verify your protective device settings. And this includes elements that we don't think have the ability to change, which could be breakers, which could have been swapped out, and even molded case circuit breakers swapped out with different values, larger or smaller. It could be fuses that we unnecessarily or inadvertently changed manufacturers or fuse values on different phases. So we need to check to make sure the fuses match both manufacturers and part numbers and across the phases. And then we've made a request to the utility company for updated information. And while it may be less convenient, the whole bottom line is to focus on safety, which is the purpose of the arc flash study itself. So number 9 is labels. Labels are a source of a lot of errors, a lot of mistakes. And they can come in all shapes and forms. And some of the mistakes are driven by the corporate policy or what we want to show or what we want to display. And that's part of the purpose of trying to deal with the political environment that we conduct these studies in, and that is there may be a certain agenda on the part of the company contracting the study or the facility, and consequently that can impact what's displayed on the label. Well, during a recent arc flash workshop, I had an electrician raise his hand and said, "Hey, Jim, when I walk up to a panel, the label says the working distance is 18 inches, but when I reach inside the panel, my hand is 6 inches from the buswork. Shouldn't that label show that energy?" Well, I thought about it for a second, and I kind of asked him, what is the purpose of the data on the label? And even better, who is the target audience for that information? And he was a little slow to respond, so I held forth with my way of thinking, and that is, think about this. Labels tell us the arc flash boundary, and that's the area, the limit, within which only qualified workers are allowed. So do labels authorize hot work? Do they tell us anything about the maintenance that's required on that piece of equipment? When you think about it, the labels are there to keep the unqualified chuckleheads out of the area when things are open. And in some regards, probably a better label might be something along this mindset. And the whole point of the label is to alert people that there's a hazard involved. Now, the working distance, the main reason to put instant energy and working distance on the label is to let qualified people know what to expect if the cover's off. Now, that doesn't tell me anything about the hot work. That doesn't tell me anything about the actual requirements of the maintenance. All that falls into the purview of the hot work permit. And this is something I've come around full circle on. I used to think a hot work permit was just a piece of paperwork that you had to sign off to deal with the government regulations or to deal with company policy. Well, it turns out if you really understand the purpose of an arc flash study, the hot work permit is the first place you go when you want to improve the safety of the working conditions of the workforce. And once you have an understanding of what the procedures are that are required, the maintenance that's required, and have a discussion between management, and there's an understanding of what the acceptable risk and hazard to the employee that the company will support, then that will dictate what the PPE that I need to use and the working distance that would be required or expected for a specific procedure. So it's a good place to start thinking about really what the label is for, and better yet, how important the hot work permit is. So then, taking this a step further, if labels are for qualified workers, then the more information is the better. Well, again, I think labels really are not focused on qualified workers, so let's kind of dig into this a little bit deeper. NFPA 70E says in Article 130.5H that label requirements shall include nominal system voltage, arc flash boundary, and at least one of the following. And so this could include available incident energy, or if we have not done a study, not done a calculation, the PPE category from the lookup tables, or minimum rating of the clothing, which is incident energy, or a site-specific level of PPE. Now, it's important to notice on these first two elements, the NFPA specifically says we can't put both the available incident energy and the PPE category. Well, in the old days, here's the way it used to work. We would calculate the incident energy, and we take this table, and if that incident energy fell below these two columns, of the lower energy and the higher energy, then that dictated or told me what category of PPE I needed to wear. Now, this table has not only been not allowed and no longer available in the standard, the term HRC is no longer allowed, and we cannot use it in reference to any designation of the PPE. Well, as soon as I put this into my presentation, the first question I get back is, wait a minute, what do I do if all of my system is based on HRC? HRC being hazard risk category. My safety manual is based on HRC. My labels all have HRC. My PPE is even segregated by PPE rating or HRC rating. Why the change? Well, in my opinion, some people are not getting the message because we're taking the understanding of the hazard out of the equation, and we're just basing everything on category numbers. If the arc flash PPE rating is based on the premise that the worker may get burned at least half the time they will recover, if you think about what the regulations are, the PPE ratings stipulate their protection down to, at best, 1.2 calories per square centimeter. That number is based upon the level of energy that it takes to create or develop second-degree burns, and that's an acceptable level of damage because at least the worker will heal with minimum scarring. Now, if my company's really committed to the safety of the worker, this may not be good enough, and especially I, as the person doing the work, if I'm disregarding whether or not the PPE is covering the energy produced or potential energy that could be produced in a mistake or an accident, why would I disregard what that incident energy is? So it seems that NFPA 70E intends for qualified workers to really understand what the level of protection that they're really dealing with, and to find some common ground in understanding what that means. So the bottom line is the information on the label should be understood by both the rank and file as well as the people or the management that are dictating the content of the label. And at the bottom line, what do I do if I have labels that have HRC on them? All my PPE has HRC on it. My safety manual has HRC. Am I instantly out of compliance? Well, I think the bottom line here is that the Standards Committee, the government, OSHA, and NFPA don't expect things to change overnight, but the fact is our labels are non-compliant, even though our study may not have changed at all. What do you do about that if you realize it's going to take some amount of time to change the labels, it's going to take some amount of time to change the PPE labeling or rating? The thing to do, first of all, is establish the timeline to accomplish those changes. But more importantly than that, during the next safety meeting, explain to the rank and file why things are being changed and the importance of understanding what incident energy is and how the incident energy affects their safety, and the only way to assure that they will be able to reduce the hazard risk involved is to understand the incident energy numbers on the label must be exceeded by the rating of the equipment that we're pulling from the PPE locker. So that's the top 10 mistakes. Thank you all for attending the presentation. Invite you to check out the website, and we'll talk to you later.